The last video we were using a new right-hand rule to determine the direction of an induced current in a loop or coil of wire due to a changing magnetic field. So all those examples we were just determining the direction, and there was really no formula for us to calculate the current or anything like that. We were just looking for the direction of the current through a loop when we introduced a changing magnetic field. But the induced current is actually a consequence of the induced voltage inside that loop due to the changing magnetic field. So we call this induced voltage an electromotive force, or EMF. So it's kind of a misnomer. It's not a force. This is actually a potential difference. Right? So there's an induced potential difference inside a loop due to a changing magnetic field. So we use this capital kind of cursive looking, I don't think it's technically cursive, but it's like a scripty looking E. Sometimes you'll see capital V with a subscript EMF to denote the induced voltage. And this is Faraday's law. So if there is a changing magnetic field through a loop, in particular if we actually have a change in flux. So we're going to talk about some situations where the magnetic field isn't changing, but something else about the situation is changing to induce a voltage. And so the induced voltage is directly proportional to the changing magnetic flux through the loop or the coil. So you remember this capital phi, that was the dot product between the loop's area vector and the magnetic field vector. So if there's a change in flux over time, there is an induced voltage in this loop or coil. This N, if you remember back in chapter 19, we were talking about the torque on a current carrying loop. If there was more than one loop in that coil, then we had to multiply that torque by the number of loops in the coil. And we're going to do the same thing here. So the induced voltage is also proportional to the number of loops in the coil. Okay, and so the negative sign denotes the direction of the induced voltage, so that an induced current is driven through the loop, and the direction we determine by using our right-hand rule and Lenz's law. So the flux depends on three things: the magnetic field changing, the area vector changing, and the angle between those two vectors changing. So basically our examples are going to contain one of these quantities changing over some time interval. And so we're going to calculate the change in flux, and then if we're given the number of coils, we'll use, or the number of loops, we have the number of loops, and if we're given a time interval, we can calculate the induced voltage. So the first thing we would do is we're going to find delta phi. Okay, so we're going to find delta phi by calculating AB cosine theta, and we're going to calculate two of these, right? Maybe not two entire fluxes. Maybe if just the area is changing, we'll calculate the change in area, we'll calculate the changing magnetic field, or the change in the angle, right? So once we calculate that, we can actually just substitute that in there, and then we'll get a delta phi. So the first thing we're going to do is calculate the change in flux. Watch for an area that's decreasing, or a magnetic field that's decreasing. So that would give me a negative delta phi. So it would give me a negative delta phi, and that negative sign would cancel out with this negative sign, and we'd get a positive EMF. Okay. So first thing we'll calculate delta phi, then we'll calculate the induced voltage, and finally, if we're given the resistance, or maybe some properties that allow us to calculate the resistance. Remember that resistance is the resistivity of the material times the length divided by the cross-sectional area, if we're talking about a wire. So if we have those properties, we can calculate the resistance, and then we can actually find the magnitude of the current by using Ohm's law. So we'll take the induced voltage divided by the resistance, and then we'll get the current. And then finally, we'll use the right-hand rule to find the direction of the induced current. Let's take a look at our first example. We've got a coil that has 25 loops of wire. So N is 25. Right off the bat, I can see N is 25. And it's got a cross section of 1.8 centimeters to a side. So it's a square loop. So it's 1.8 centimeters times 1.8 centimeters. So I have the dimensions, and I can use that to calculate the area, because the first step is going to be to calculate the flux. The total resistance is 0.35 ohms. That's good, so I don't have to use rho L over A to calculate the resistance. There's an applied magnetic field in the positive Z direction. So it's perpendicular to the coil, so there's a magnetic field passing through the coil in the positive Z direction. So there's a change from 0 Tesla to 5 Tesla. So that's B initial, that's B final. So I'm going to be calculating a delta B. I'm going to be calculating my change in magnetic field. It's going to be in the positive Z direction. You see that B final is 0.5, B initial is 0, so delta B is going to be positive 0.5. So it's increasing in this direction. Now that tells me when I'm on my last step trying to find the direction of the induced current, delta B is going to be in the positive Z direction. That means B induced is going to be in the negative Z direction. So that induced magnetic field direction is what I'm going to use along with the right-hand rule to find the direction of the induced current. And so it takes 0.8 seconds for this magnetic field to change. So there's my time interval, my delta T. So I'm ready to use Faraday's law to calculate the electromotive force, the induced voltage, and then I'll use Ohm's law along with the resistivity to find the magnitude of the induced current, and then use the right-hand rule, knowing that B induced is in the negative Z direction, to find the direction that the current is passing through that loop. So 25 turns in the coil. The area is, it's a square loop, so it's one side squared. I converted it to meters, so I get 3.24 times 10 to the negative 4 square meters for the area of the loop. The resistance, 0.35 ohms. So I wrote B initial is 0 Tesla, B final is 0.5 Tesla, delta B is B final minus B initial. So that's a 0.5 Tesla. I've got a time interval of 0.8 seconds. If I go back to the diagram, the area vector is perpendicular to the surface of the loop. So A is in the same direction as B. So the angle between my area vector and my magnetic field vector is 0. Cosine of 0 is 1. So my flux term is at a maximum. It's not a function of the angle. And this loop isn't going to rotate, so I don't have to worry about that cosine theta term in this problem. So A and B are in the same direction, so A dot B, or the cosine term inside the dot product, is 1. So cosine 0 is 1. So I'm ready to calculate the change in flux, which is delta B times A times cosine theta. So if only one of these terms is changing, theta, B, and A, all I have to do is write that change in for one of those terms. And in this case, the only thing that's changing is the magnetic field. So this is delta B, this is A, and this is cosine theta. So that's my change in flux. That's my time interval, the time it takes for the magnetic field strength to change. And that is the number of coils, or loops in the coil. So I calculate this, I get an induced voltage of negative 0.005 volts. So very small induced voltage. Now I'm ready to use Ohm's law the current is the induced voltage divided by the resistance, so negative 0.005 volts divided by 0.350 ohms, and I get negative 0.014 amps. So we're just going to leave the negative sign, it's fine. I'm going to use the right hand rule to determine the direction of the induced current. So delta B is in the positive Z direction. That means B induced is in the negative Z direction. So I'm using my right hand. I'm going to point my thumb down in the negative Z direction. Excuse me. Point my thumb down in the negative Z direction and then curl my fingers around the coil like I'm grabbing it from the outside. And when I curl my fingers around the coil, I have an induced current in the clockwise direction if I'm looking down at it from above. So the thumb of my right hand was pointing down, my fingers curled around the loop in the clockwise direction. So that's the direction of the induced current. So if we ask for, if a loop is situated like this and we're asking what the direction is, our convention is clockwise or counterclockwise based on if we're looking down at it. Like if we're above the loop and we're looking down at it. So that's our convention. Because if I was under the coil and looking up, it would be a different direction for me. So we're always above it looking down, and that's how we determine the direction of the induced current, or that's how we describe it. So we have a concept called motional EMF, and what we're actually doing here is we're not changing the magnetic field strength. So we have a loop or a coil inside a constant magnetic field, but we have a change in area, right? If we have this bar, right, we have this bar that's a conductor, so we'll have a current going through this loop. If this bar is pulled, it's allowed to slide. If this bar is pulled in this direction, the area of this loop or coil is changing. So it's increasing in this case, right? We've got a speed V, right? We've got this speed, this bar is moving this direction with a constant speed V. So the area of the loop is increasing. So we have a delta A, which means we're going to have a change in magnetic flux, which means we're going to have an induced voltage. Okay, so let's talk about this situation. The resistance of this loop is 6 ohms. Again, we're given the resistance, that's good. This length L, so the length of this bar is 1.2 meters. And there's a uniform magnetic field of 2.5 Tesla directed into the page. So this is very similar to this diagram right here. So it's a constant magnetic field into the page. We've got a rectangular loop, okay, so we've got an L, and then we've got these dimensions down here, which I don't see what they are yet, okay. It says, what speed should the bar be moved to produce a current of 0.5 amps in the resistor? So we're actually looking for the speed here, okay. That's kind of strange because we don't see any velocity terms in any of our equations yet. But we do have a set induced current. So we need the current through this loop to be 0.5 amps. And we've got a resistance, so we can actually calculate the necessary induced voltage that will result in a 0.5 amp induced current. So we need to find the speed with which we move this bar in this direction. So we don't have speed, but speed isn't in our expressions, and we don't have time, which is kind of strange. So I'll start by just writing down everything I have. Okay, I've got a resistance. I've got the length, right? I've got the length of this side of the wire, but I don't have this length, right? I don't have the horizontal dimension of my loop, but I know it's going to be changing, right? When you move that bar to the right, it's going to be displaced some distance delta x, right? I don't know what the original dimensions are. So I won't be able to calculate the original area, but I can write it in terms of how it's changing. So that's what I'm going to do. The first thing I'm going to do is I'm going to calculate the required induced voltage using Ohm's law. So 0.5 amp current is what I need inside the loop. It's got a resistance of 6 ohms, so I need an induced voltage of 3 volts. So here's what happens. The bar is being pulled in this direction, and so it's going to have a constant velocity in this direction. So from 120, the velocity of this bar is going to be delta x over delta t. So it's the horizontal displacement divided by time. So when we move the bar to the right, it undergoes a displacement. Okay. Now I don't know what x final is, and I don't know what x initial is. If we go back to the diagram, we aren't given these dimensions, but that's okay, because I don't actually have to know the area. I don't have to know the cross-sectional area. The only thing I have to know is how the cross-sectional area is changing. So the change in the area of this loop is going to be the length, right, this vertical dimension right here, times how the horizontal dimension is changing. Okay, so my change in area is just the length times delta x. Okay, so I don't have to know those dimensions, I just have to know how that horizontal distance is changing. Again, the area vector and the magnetic field vector are parallel to one another. The magnetic field is going into the page, and the area vector is perpendicular to this surface. So again, theta is 0, so cosine theta is 1. I don't have to worry about this term. Okay. So let's substitute our expression in for delta A. I know the area is changing, the magnetic field is constant, and the number of coils is always constant. And I believe it's not giving us any number of loops, so we're just going to say n is equal to 1. So this is 1 bar, and it's a single loop, so n is going to be equal to 1. So I substitute L delta x in for delta A. That's right here. But we see we weren't given a time interval, but we have this term delta x in the numerator and delta t in the denominator. So that is v. That's our velocity right there. So I'm going to take that delta x over delta t, and I'm going to substitute v in for that. And now I've got a new expression for the induced voltage. That's E is negative N B L V. So this V term is what's causing the change in flux, because this velocity has my delta x term in it, which in turn results in a changing area. So it's an increase in the area. So I'm looking for the velocity, right? I have the length, I've got the constant magnetic field, the number of coils we'll say is 1, and I calculated the induced voltage using Ohm's law. So I can solve this for the velocity. So I solve this for the necessary velocity, divide both sides by N, B, and L. Substitute my values in. 3 volts was the induced voltage necessary. Constant magnetic field at 2.5 Tesla. My length was 1.2 meters, and I get a speed V of 1 meter per second. Okay, 1 meter per second. So I was just asked for the speed. So there's a change in area. There's an increase in the area. So delta phi is positive, but I have this negative sign here. But I'm just concerned with the speed in this case. So that's what we call motional EMF. We can move this conducting bar inside of a loop. We increase the area, the surface area, in the presence of a magnetic field, and we've got a change in flux, so we have an induced voltage. So here's another induced voltage problem. We've got an equilateral triangle, so that means all the interior angles are 60 degrees, so that's going to be helpful. The lengths of the triangle are 2 centimeters. Actually, you know what I'm going to do? That looks like a typo, so I'm going to go to my solutions, and I see that I used I use 2 centimeters here. Okay, so I'm going to use 2 centimeters. Sorry about that, the diagram says 20. So I'm going to go through and I'm going to use 2 centimeters. Sorry for that little typo there. Okay, it's halfway into a 0.1 Tesla magnetic field. So that means half of the area that this triangular loop makes is in the presence of a uniform magnetic field. Okay, so I'm going to calculate the magnetic flux. Right, so I'm going to calculate delta phi first through the triangle. So that's the magnetic field strength times the area of the loop that's in the presence of the magnetic field. Now the difference between this problem and previous problems is that only half of the triangle is in the magnetic field. So I'm only concerned with this area right here. So I'm going to calculate the area of just the triangle that's in the presence of the magnetic field. So part B says if the magnetic field decreases, what's the direction of the induced current? So I'm using the I'm going to use the right-hand rule to determine the direction of the induced current in this loop. Okay. So I've got a uniform magnetic field into the page, right? And it's 0.1 Tesla. So I'm going to calculate the entire area of the triangle, and then I'm going to split it in half to get the area of the triangle that's just in the magnetic field. So I take a straight line, right? This is a perpendicular bisector from our old geometry days. So this line right here splits this equilateral triangle into two 30, 60, 90. So that's going to be 60 degrees, that's going to be 30 degrees, and that's going to be 90. So what you can do is you could just calculate right off the bat, you can just calculate the area of half the triangle, right? So the area is 1/2 the base times the height. So you can just say 1/2 times this base, 1 centimeter, times this height. This is a 30, 60, 90, so x root 3, 2x. Okay, or you can use the Pythagorean theorem. I've got this side, I've got the hypotenuse. I can use the Pythagorean theorem to find the height of the triangle. So again, what I did was I calculated the entire area of the triangle, and then I divided it by 2. So I get root 3 over 2 times 10 to the negative 4 meters squared. If you've got a decimal, that's fine. You can work with that, no problem. So I've got the area, I've got the magnetic field. Again, the area and the magnetic field are acting in the same direction. Those vectors are parallel. So cosine of 0 is 1 again. I don't have to worry about that. So I'm just calculating the flux, right? The flux. So substitute B in, substitute the area of half the triangle, and I get 8.66 times 10 to the negative 6 Webers. Tesla meters squared is a Weber. All right. And maybe, you know, you can say something like, if you want to turn this into a different problem, you can say in 2 seconds the magnetic field moves to where the entire triangle is in the presence of a magnetic field. So you could calculate delta A, right? You could take the whole area of the triangle minus half the area, you'd get delta A, and make up a time interval, 2 seconds, 5 seconds, something like that. You can calculate the change in flux, and then you can actually find the induced voltage. Okay, so if you had a time interval and you made the area in the presence of the magnetic field change, you could turn that into a full Faraday's law problem. So the magnetic field is decreasing. Okay, so B initial is going into the page. B final is still going into the page, but it's going to be weaker because the magnetic field is decreasing. So that means delta B is in what direction? Delta B is towards me. Okay, magnetic field is into the page, but it's decreasing, so delta B is coming out towards me. That means the induced magnetic field is into the page. So the induced magnetic field as a result of delta V, which is out of the page, is going back into the page. Right hand rule time, thumb into the page, curling the fingers of my right hand around the coil, and I'm turning them in the clockwise direction as I'm looking at the computer screen. So my induced current is clockwise around the loop. Clockwise around the loop. Alright, so this problem, as you can tell, we've got some copyright information, so I like to steal problems. On occasion, I've been known to do that. This is very similar to a WebAssign problem. This looks very similar to a WebAssign problem. So if we go back all the way to like one of our first Faraday's Law slides, it's like this, right? It's a situation very similar to this. So we have a circuit that's connected to a battery, and it's got a switch. So we're going to we're going to close the switch, and then we're going to leave it on for a while, and then we're going to open the switch back up, and then we're going to see how this the magnetic field generated by this coil induces a magnetic field in this coil, and then we're going to use our right hand rule to find the direction of the current. So that's what we're doing in this problem here. Okay, so this is our this is going to behave like our bar magnet. Okay, this is going to be our bar magnet. So when we close the switch, when we close this switch, there's going to be a current. So this longer line right here denotes the positive end of the battery. So we're going to close this switch, and then there's going to be, as soon as we close the switch, there's going to be a current in this direction, right? Current from positive to negative. So this current's going to go this way, and it's going to go up. Another reason I like to steal these problems is because the diagrams are a lot nicer than I can draw them. So we got to pay attention to the direction that the coil is looping around this bar. So we've got a current in this direction. It goes behind the bar. You see how it's going behind the bar, and then it's coming up around, and then it's going back behind it, and then around again, right? We've got a bunch of loops, and then it's coming back down. So we need to find the direction of the current in this through this resistor. So there's going to be an induced magnetic field in this coil, which is going to generate an induced current in this loop. So we have to find that direction. So part A is the instant the switch is closed. The instant the switch is closed. So with the switch open, there's no magnetic field. The instant we close this switch, there's a current going through like this. So what I need to know is what is the direction of the change in the magnetic field in this coil, because this delta B from this coil is going to cause an induced magnetic field in this coil. So let's use our right hand rule, and we are going to grab onto this coil, but we have to curl our fingers in the direction of the current. So you see the current is going behind the loop right here, or behind the bar right here, coming out like this, going back behind it. Okay, so if I was standing over here and if I was looking at the bar magnet, it would be counterclockwise. Right? Kind of hard to picture on a 2D piece of paper. But if I was over here looking to the left, I'd have a current going this way. So that's the direction I'm going to grab that bar. So I take my right hand, I'm going to grab the bar. Picture yourself grabbing the bar from underneath. Right? If you grab the bar from underneath, your fingers are going to loop around behind it, just like the direction of the current. So we want our fingers to curl in the direction of the current. So my thumb right now is pointing to the right. My thumb's pointing to the right. What that means is that is the direction of the changing magnetic field in this coil. So delta B is in this direction. Alright. So the induced magnetic field in this coil has to oppose the changing magnetic field it experiences. So I'm going to take the same hand, right? I've got my hand, and I'm grabbing onto the bar on the left, and my thumb is pointing to the right. That's delta B. So now I have to flip my hand. All I have to do is flip my hand 180 degrees. My thumb is now pointing in the direction of the induced current, or the induced magnetic field, excuse me. So B induced in this coil is to the left. The induced magnetic field is to the left in this coil. So I'm going to use the right hand rule again. My hand's already here, right? My thumb is pointing to the left. So my fingers are curling in the direction of this induced current. Now this is a little hard to follow here, okay? But your fingers should now be looping over the back of the bar like this, right? So they're looping over the back. So I'm grabbing it, but the top of my hand is facing me, and my thumb is to the left, the direction of the induced magnetic field. So you see that my fingers are curling over, they're curling over, they're curling over, they're curling over, and then this part of the wire is behind the bar, and it's coming down like this, and then it's passing through like this. So the induced current right here is to the right. The induced current, the instant I open the switch, okay, I've got an increase in current, which means I've got an increase in the magnetic field to the right. I've got an induced current to the left, or induced magnetic field to the left, so the induced current goes around the loops like this, comes back around the back like this, down and through the resistor to the right. Okay, and these are my poorly drawn sketches. I tried to do them as best I could. Okay, so my induced current goes that way. The right hand rule tells me delta B is to the right. My induced magnetic field is to the left, so my current is looping in this direction. I induced is to the right. Okay, so that's part A. Part B, it says after the switch has been closed for several minutes. Now what this means, and we'll see this in Pre-Lab 9 and Experiment 9, when we use that simulator, when you put the bar in that coil and you leave it there, that the current meter goes back to 0. Okay, so what's happening here is something similar, right? The switch is closed for a very long time, so that means we still have a current going through this coil, right? We still got a current going through this coil, but that current is constant. Okay, the current's not increasing, the current's not decreasing. We've got a constant current which is generating a magnetic field inside this coil, but now that magnetic field that has been generated as a result of that current is constant, right? We've got a constant current, we've got a constant magnetic field in the positive X direction. So what that means is if the magnetic field's not changing, there's no delta B. If there's no delta B, there's no B induced. So the magnetic field has to be changing. Those first three examples when we introduced Faraday's law show that the magnetic field has to be changing, or the area of the loop has to be changing, something like that. So my magnetic field now is constant after the switch has been closed for several minutes. So there's no induced B field here, and there's no current. So part B, there's actually no current passing through the resistor because the applied magnetic field is constant. Part C, we're going to open this switch. We're going to open this switch. So that means that current that was running through for several minutes is now going to decrease to 0. All right. Now the current's still flowing in that direction, but it's decreasing. Okay, so the direction of the change in current changes. So that means as this current decreases, the applied magnetic field that was in the positive X direction is now decreasing. Right? So that applied magnetic field is now going to 0. So B initial is in the positive X direction, but B final is 0. So 0 minus the initial B field. The delta B in part C, when we open the switch, delta B is actually in the negative X direction now. So since the magnetic field to the right is decreasing, delta B is to the left. So I use my right hand rule again, except my thumb is going to be pointing in this direction for delta B. So on this bar right here, I'm grabbing the wire, or I'm looping my fingers around the wire with my thumb in the direction of delta B, which is to the left now. So I know delta B is to the left. I've got to switch it to find the direction of B induced. So I rotate my hand 180 degrees. Now my thumb is pointing to the right. That's the direction of B induced. That's the direction of the induced magnetic field in this coil. So my thumb is pointing to the right. What's the direction that my fingers are curling around this coil? So I'm actually grabbing the coil from underneath, and my fingers are going around behind it, right? They're going underneath the bar, and they're going up around and coming around like this, okay? So that means it's going like this. The current's going like this, going back behind it, current's going like this, going back behind it, current's coming up over, and then it's going to the left. So with a decreasing magnetic field due to this bar, B induced is now to the right, and the current is going to the left. So the induced current has switched directions, okay? So delta B is in the negative X direction, B induced is in the positive X direction. And so same diagram, except we're grabbing the wire from underneath. We're grabbing the coil from underneath. So it's looping around like this, and then it's coming out like this. And then it's going to the left for part C. Okay. So that's, again, this is pretty similar to a web-assigned problem. So study that. Use your right hand rule, find the direction of delta B, switch it, that's the direction of B induced. Use that right hand rule, grab the wire, find the direction of the induced current. Okay, so I've got one last problem, which I should have enough time to cover. So I'm going to give that a try. So I've got a square loop, okay, and it's got a total resistance of 10.6 ohms. It's in a uniform 0.14 Tesla magnetic field, so B is not changing. The loop is pulled at these two corners, right? So what's going to happen is it's going to turn from a square, and then it's going to become like a quadrilateral, right? Like a rhombus, right? A rhombus has, you know, all four congruent sides, right? So it's going to become a rhombus, so that means the area is going to change. Okay. The separation between points A and B is going to be 0.3 meters. Now we see it's a square loop, right? 0.3, 0.3, 0.3, 0.3. This is, or excuse me, 3. Sorry. So 3, 3. This original distance is actually 3 root 2. So I'm going to calculate the original area of the loop. I've got a time interval, 0.104 seconds. So I'm going to calculate the initial area of the loop, and then I'm going to find the final area of the loop when I stretch, when I pull these two sides out. So the cross-sectional area of this loop is going to change. So my magnetic field is constant. Okay, I've got a constant magnetic field of 0.14 Tesla, a resistance of 10.6 ohms, and my initial area is 9 square meters. So 3 meters by 3 meters, 9 square meters. So the time interval from where the area changes is 0.104 seconds. Let's find A final. So we stretch the loop, okay? We stretch the loop, and the distance between the top corner and the bottom corner is now 3 meters, okay? So what I have to do is I have to find this area. So what I did was I found the area, since I don't remember the formula for the area of a rhombus, and even if I did, which I think I do, I have to know this diagonal, which I don't know. So what I'm going to do is I'm going to find the area of this top half, right? I've got the base of this triangle, okay? I've got the base of this triangle, and I've got these two sides right here. So all I need to do is find that height. So it's going to be a right triangle. I think I can find that height using the Pythagorean theorem. So if this is 3 meters, or excuse me, this is 3 meters, the height is actually half of those 3 meters. Okay, So this height is 1.5 meters. I need to find that base actually. So I need to find the base. So here is this is actually the area of 1/4. Right? See this triangle that I have starred here? That's actually the area of 1/4. So actually you can take this and you can multiply it by 4, and then you would get the whole area of the rhombus. Okay, so a couple different ways you could do it. You could find this quarter, multiply it by 4. You can find this half, multiply it by 2, whatever you want to do. So I used the Pythagorean theorem to find the base of this little one, right? And the base of this little triangle is 2.6 meters. So if you double this, you've got the base of this entire shaded triangle right here. So now you have the base of the entire shaded triangle. So I'm going to use 1/2 base times the height, and then I'm going to multiply it by 2 because I want the area of 2 shaded triangles. So I want this multiplied by 2. So I've got 1/2, my base is 5.2 meters, my height is 1.5 meters, multiply it by 2, my new area is 7.8 meters squared. So A final is actually less than A initial. So delta A is going to be negative. So delta A is 7.8 meters squared minus 9 meters squared. And that gives me a change in area of negative 1.2 meters squared. Let's calculate the change in flux, and then I'll substitute that in for Faraday's law, and I'll get the induced voltage. Constant magnetic field, my change in area. Again, my magnetic field and my area vector are parallel to each other. Once again, I don't have to worry about an angle change. So my change in magnetic flux is negative, because I've got a decreasing area, negative 0.168 Webers. So when I substitute that in, my negative signs will cancel. It's a single loop. I've got my time interval of 0.014 seconds, and I get an induced voltage of 1.62 volts. Finally, I'm looking for Ohm's law. So the current is the induced voltage divided by the resistance, and I get an induced current of 1.5 amps. And for a little bonus, right, we don't know the direction of the magnetic field, but you can, for practice, you can put the magnetic field into the page, put the magnetic field out of the page. You see that the area is changing, and then you can use your right hand rule, see what direction B is, or the flux is decreasing, right? Because if your area is decreasing, you have fewer magnetic field lines in the loop. Okay, so whatever direction B is in, whichever direction you want to put B in, you can find the direction of the induced current using the right hand rule. Okay, so that's just a little extra practice if you want it. And that's the end of chapter 20. I also put some extra videos in there from people who can like record themselves and use their hands and show you the right hand rule a little better. If you want some more explanation, go ahead and email me. We can Zoom. I can show you how to use the right hand rule as best I can through Zoom or something like that. Okay, so again, let me know if you have anything. That's the end of chapter 20, so reach out if you got any questions or concerns. All right, thanks, see ya.